Okay, AP students, welcome to my first attempt at screencasting here. So I'm going to pull up our notes. Hopefully those pop up. And make this full screen for you. And we're just going to go through two sections on limiting reactants and percent yield, so we can work on some of those practice problems tonight, even though we had lab today. So first of all, limiting reactant or limiting reagent, either of those mean the same thing, reactant or reagent. You'll probably hear me in class usually refer to them as reactants. Switch to pen, reactants, but they can also be called reagents. So the big idea here is that in a reaction, when there's two reactants that are mixed together, two random amounts, the amount of product is limited by whatever you run out of first. In real world reactions, you're not likely to use all of both reactants at the same time down to the last atom. So you'll always have insufficient amounts of one reactant to completely react the other. So we'd say it's limited by whichever one's consumed first. That reactant is referred to the limiting reactant. The one that is left over is what we call the excess reactant. So if you're given quantities of two reactants, you can actually calculate how much of each product you would be able to make. The one that runs out first is the one that could, if I can zoom in here, could make less. It's the one that could make less. It's the one that you're going to run out of first in a reaction. Okay, so we're going to look at practice 3-10 on page 96 in your textbook. So if you flip to that, it's worked out there, but we're just going to kind of walk through it, and I'll show you how I would approach something like this. So if you look at 3-10, it gives you a reaction, and it tells you the amount of both reactants. It tells us that there is 25.9 grams of the nickel 2 chloride, and there is 10.0 grams of the sodium hydroxide. And these are both the reactants in that reaction. And it's asking for how much of that product, the nickel 2 hydroxide, could be produced. So what we're going to do is we're going to take both of these two different products, and we're going to do two separate stoichiometry calculations. And we're going to try to find, in both cases, the grams of nickel hydroxide that we could make. And if you recall from our dimensional analysis, or stoichiometry, or mole house, whatever you did in regular chem, we're going to need three steps here. The first step is going to be to convert grams of NiCl2 into moles of the NiCl2. And then anytime we have moles to mole, like we have to convert from one substance to another, we'll need to use our mole ratio. So this one would be the moles of the nickel chloride. And here's where we convert from moles to the nickel hydroxide. I apologize, that's tiny. Looking at our balanced equation, there is 1 mole of nickel hydroxide per 1 mole. So that's nice and easy. We've got a 1-to-1 ratio there. And then lastly, we use our molar mass again. 1 mole of the nickel hydroxide for the grams of the nickel hydroxide. Now I'll let you work through these numbers or just take a look in the book. But the numbers come out to, oh, well, in the book they do it to moles. That would be acceptable. But we could find the numbers of grams, and it would turn out that this number here, switch to a different color to emphasize what I'm doing here. This number here that we would find, this would be lower, and this number here would be higher, indicating that with 25.9 grams of nickel chloride, we could make less of the product. So once we've made that amount of product, which I think comes out to 11.6 grams in the textbook, doesn't actually calculate the other, but 11.6 grams, we're going to be out of the nickel chloride. If we have no more nickel chloride, the reaction stops, and this is not possible for us to make because we've run out of nickel chloride. So we would identify this as the limiting reactants. We identify this as what is actually produced. And we would identify this as the excess reactant. And this number down here, we actually wouldn't end up caring about what that number was because it's more than what we would be able to make. So you can see the second part of this problem says how many grams of the excess reactant, So for us, that means the sodium hydroxide remaining after the reaction is complete. Now, if we know that we started with 10 grams, figure out how much is left, we need to figure out how much we used. So previously we just found that we're going to produce 11.6 grams of the nickel hydroxide. Nickel hydroxide. So with that, we can convert that. So this is how much is produced. We can kind of work backwards. If we're actually going to produce that much nickel hydroxide, we can work backwards and say, okay, well, how many grams of NaOH would I need to use? Okay, and I can walk through that calculation, and I get some number of grams here. Okay, for the sake of the video, I'm going to let you pause and figure out what that number is. But we do the same thing as we've done before. We do our dimensional analysis, so you'll have I'm going to abbreviate here. I'm going to use a molar mass to get moles of nickel hydroxide. I'm going to use the mole ratio, which in this case will be, it looks like a 2-to-1 ratio, and then I'll do the molar mass. But I'm not done yet, because this is how much was used. Okay, so if you think about it for a second, if we know how much we started with and we know how much we used, hopefully you're coming to the same conclusion that all we need to do is a simple subtraction. So to figure out how much is left, we need to do the 10 grams we started with. Okay. Oh, it should be 3 sig because there's a side note. Minus however many of grams that we used gives us how much is left over. Okay, and you get your answer for that. And that is how much of the excess should be left when the reaction is complete. Again, it's left over because we ran out of our limiting reactant, nickel chloride. So, in a real reaction though, it is very unlikely that all atoms will actually meet all other atoms to react. So in an actual reaction, we have what we call the experimental yield. The experimental yield is only found through an experiment. You have to do a lab to be able to get this value. So in the problem, this will be given, or if we do a lab on this, or when we do a lab on this. Experimental value yield is how much actually reacts. Theoretical yield is how much you should get. Okay, and this would be calculated, and this will always be the bigger value. Again, because not every single atom will react, so our experimental yield in a real reaction would be less than that theoretical yield. The percent yield is simply a ratio of the two. Our equation for percent yield, if you remember, percentage is the part over the whole. So percent yield is the part that we made, which would be our experimental yield, over the whole, which would be our theoretical yield, and I'm abbreviating for the sake of space, and then times 100. To do the example, it's 3-11 on page 97. It tells us a 15.6 gram sample of that C6H6 is mixed with excess HNO3. By saying that excess, it's telling us that HNO3 is not the limiting reactant, so we know that the C6H6 is the limiting reactant. We isolate, meaning produce, as a product in the reaction, 18 grams of the C6H5NO2. What is the percent yield? So you can see that the first thing they do there is they take that 15.6 grams of the C6H6, and they're going to do their mole conversions to figure out how many grams of that product, the C6H5NO2, should be produced. This value would then be the theoretical value. This is the theoretical yield. Again, sorry for abbreviating. Okay, so we can do a molar mass, we can do a mole ratio, and we do our molar mass one more time for the C6H5NO3. That number, as a check, should be less than 18. And if you take a look at the example, they work it out, and they get that it comes out to 24.6 grams of this stuff, which is, excuse me, did I just say less? Is greater, because the theoretical yield is greater. I'm sorry, I forget if I said more or less here, but the theoretical yield should be greater. So to find the percent yield, we simply do the experimental yield, which the problem gives us, because we can't do a lab, obviously, when we're doing our homework. 18 grams experimental over our 24.6 grams theoretical times 100, and that gives us 73.2%, meaning only 73.2% of the atoms that could react actually reacted and produced that product. There were no other byproducts, there was no other things that were produced in this lab. So that should be everything you need for the homework for tonight. You can see there's some other exercises. We'll get the sequential reactions later. Hopefully you find this helpful. Let me know what you think. If you want to shoot me a quick email or something, this might be something we should start doing a little more often. So you can do the notes at home, and then in class we can focus on practicing and working together. So thanks guys, hope you get something out of this. Good luck on your homework. We will have the test on Thursday, and lab will be something that we focus on after that.